Hi, everybody. My name is ZnTe, and I am really honored to be finally presenting at my own CSGF symposium. It's a shame that I won't be there in person this year and that we can't all see each other, but nonetheless, it's an honor to present at the event that I've been enjoying for the last 4 or 5 years. So first, before going into details of work that I've done during my PhD, I'll tell you a little bit about my research interests. My scientific goals are broadly centered around the methodologies of computational material science, although my PhD is in physics. And in particular, I'm interested in how we can use the tools on the left side of this slide to better discover, optimize, and understand catalytic materials using cutting-edge developments in computational software and hardware. So this is an overview of all of the work that I've done during my PhD. And one of the things that I love most about computational science is that the skill sets tend to be transferable between a wide range of different projects. So this is part of how I was fortunate enough to be able to work on projects related to two-dimensional materials, discovery of photocatalysts, developing scientific software to tie the whole thing together, machine learning for the characterization of experiments with X-ray absorption spectroscopy, and the development of machine-learned interatomic potentials that we can use to study the atomic behavior of materials over long timescales. So this is a highlight reel of all of the sort of published work that I've been a part of for each of these projects. But for the remainder of this time we have together, I'm going to tell you about probably one of my favorite projects during my PhD, and certainly the one that ended up being the most formative for my overall research interests. And this was my practicum in the summer of 2018 between my second and third years of grad school. The time that I spent in Christine Pearson's group was incredibly positive, incredibly formative. And I am really happy to talk about this work with you today because it has set the bar for the methods and problems that I've gone after ever since. So this is really where I started getting interested in energy relevant materials. Examples of those include batteries or solar cells, but this talk focuses on catalysts, which are materials that facilitate a useful chemical reaction. The name of the game is that if we have a molecule in a state A with an energy barrier that prevents it from going to a state B that we want it to be in, we can either find a way to put energy into the chemical to get it over the hump, or we use a catalyst that provides an alternate reaction pathway that makes this process easier or even spontaneous by providing an alternate pathway for the molecule to take. This catalyst is not used up and then can facilitate the reaction again and again. Now, one killer app of catalysts would be to have one that can generate fuel from carbon dioxide. These have sometimes been described as artificial leaves because they mimic the function of photosynthesis, even if the mechanism is different. Unfortunately, commercially viable catalysts like this don't exist yet, so this is where my research comes in. Basically, this work uses density functional theory to characterize the behavior of materials. And for those of you who aren't solid state physicists, the basic idea is that this realizes Paul Dirac's dream of finding approximate practical methods of applying quantum mechanics. And it took about 50 years from when he said this, but the idea is that you instead solve the Schrodinger equation using a functional of electron density rho instead of using all the electrons psi. And there's a marvelous range of properties that you can access using DFT, all of which will be relevant for this talk. They include, but are not limited to, structural and mechanical properties of materials, electronic properties like how it absorbs light or conducts electricity. They include the dynamics, like how molecules and atoms move around, or even the reactivity, which is how they interact with the surfaces of compounds. So one possible carbon neutral cycle for artificial photosynthesis could involve turning CO2 into useful fuels that then get turned into electricity, which puts the carbon back into the atmosphere for an overall carbon neutral energy cycle. If sunlight provides the energy for this reaction, then the entire thing is driven by renewable energy. So a question is, why don't we have these yet? The reason is that CO2 takes a lot of energy to break apart. The reaction pathway is very complicated, and there's many points of failure where a material can no longer facilitate the full pathway of interest. And it's hard to find materials that walk the line of stability under reaction conditions while being reactive enough to actually facilitate the thing we care about. So nobody's found a silver bullet material yet. But if you can discover new catalyst candidates, then you might have more that we can try experimentally. And so CO2 can be turned into a lot of different useful compounds, some of which are good precursors to other reactions like carbon monoxide or formic acid, or some of which are intrinsically valuable like methane or methanol for energy purposes. The reaction pathway that we'll focus on today is one that runs from CO2 to carbon monoxide via the addition of a proton and an electron twice. So we need the electrons in order to facilitate this reaction highlighted here. to be at a higher energy in the material than they would be in the molecule, so that they'll want to jump off of it to reduce the molecule. The electrons are just trying to reduce their energy ultimately. And so if we have a material such as excited electrons want to jump off, then we might have a good catalyst. This can typically occur in one of two ways. We can either apply a bias voltage to the catalyst, which sort of raises the floor of electron energy in the material, or in our case, we'll find materials where the electrons can be excited by visible light, which then facilitate the chemical reaction. Previous work out of Christine Pearson's group using high-performance computing had discovered new photocatalysts, each with their own native crystal structures, by which I mean the arrangement of atoms in space. However, the crystal structure determines a lot about a material's catalytic properties. For example, a different structure could result in better light absorption, a larger catalytically relevant surface area, or better excited electron properties. So it's always worth asking if we could find structures that do better. Now, two-dimensional structures are a class of structure that have their own special properties. Sometimes going from the 2D form, from the 3D form can improve all the categories on the right. So to clarify what I mean by this, a two-dimensional structure is one which exists in a sheet of single atoms thick. So for the rest of this talk, I'll say bulk to mean 3D structures that have atoms oriented up, down, left, right, forwards, and backwards, and monolayer or 2D structures to refer to ones that are just a single sheet thick. So the overall goal for this project is, first of all, to identify catalytic feasibility of certain structures. That is, for bulk structures, determine if two-dimensional phases can exist. So these are from previously identified candidate materials. And then the catalytic suitability. For their resultant 2D phases, try to predict their catalytic properties to see which ones might merit further computational study or even attempting in an experimental context. So our investigation of feasibility is based on gauging the stability of different atomic configurations. Each structure has associated with it a formation energy that represents the cost of bringing the atoms together in some way. We test the thermodynamic stability by ranking the candidate structures by their energy and comparing the difference between the formation energy from the monolayer to the bulk form. We want this difference between the formation energies to be small, so in order to rule out structures, we used a cutoff energy for certain to screen out certain structures. Using the 2D material literature, we found a heuristic that predicted the ability of two-dimensional materials to be stable, which turned out to be 200 millielectron volts, a unit of energy per atom. Now, we obtained these candidate compounds by starting with a previously obtained set of catalyst candidates, then running them through two-dimensional structures, which we pulled from online databases, which then gave us 36 times 8 is 288 candidate two-dimensional forms of compounds. And these were all ran using calculations on NERSC for density functional theory. So plotted here, each icon represents a structure that we tested, and note that each one above the line is rejected, each one below the line was accepted. We found 16 total structures from this initial screening that met our thermodynamic stability criteria. Now, just because two structures have a higher or lower energy doesn't say anything about the energy barrier between them. We want to also make sure that atoms that are arranged in this way, let's say, stay in this way. What I'm describing is known as the kinetics of different phases, wherein we have energy barriers between two different configurations of atoms. Computing the kinetic barriers between two different phases is not easy, but if that barrier is small, it is in fact easy to check if there will be what's called the dynamic instability, which arises when only a small amount of energy is required for a structure to change itself into a different form. To make the concept of dynamic stability clear, a house of cards is a thermodynamically stable analogy where it happens to be stable with minimal perturbations, but if you put a little energy into it, such as by banging the table, it will very rapidly change back to a lower energy state by collapsing. It's very standard to compute what's called the photon spectra, which tells you how a material vibrates. This is an efficient way to check for dynamic instability. The photon spectra comes from this equation, which is the first and only equation of this talk. And what equation 1 tells us is that the dynamical matrix D, which describes the energy cost to moving atoms around in the material, has characteristic frequencies omega, which correspond to different energies. So remember, these frequencies omega correspond to energies. And so if we can inspect the frequencies to see if they're positive, which indicates stability, or if they're squared are negative, that indicates imaginary frequencies and therefore instability. This shows a typical phonon spectrum for bulk zinc telluride. The bands describe different ways of vibrating. Don't worry about what those bands in particular mean, but the height of the curve dictates the energy associated with a given way of vibrating. For instance, this way of vibrating is higher energy than this way, and this way is the highest in energy of the three that are plotted. So here's an example of what it looks like when the phonon frequencies are negative. This means that the deformation results in a gain in energy, which is the opposite of what we want. So we want a small deformation of the structure to cost energy, which means that it wants to go back to the way that it was before. And so the good news is that we found that for 15 of our 16 structures, all of the phonon energies were positive. So looking for these spectra for gallium telluride, gallium selenide, zinc telluride, and silicon arsenide, we verified that all but one of the structures were dynamically stable. So that settles the feasibility side of the argument. We'll now move on to suitability. The three ways in which we predicted catalytic suitability were by studying the light absorption, checking to see if the excited electrons had the right energy, and then looking at the binding energy of the reactants. To start with the light absorption, if you remember from high school chemistry that atoms have occupied and unoccupied electron orbitals with a limited set of energy levels, just know that materials in a periodic arrangement or crystals have a set of bands with a similarly limited set of energy levels. In order for light to be absorbed by a material, meaning the energy difference between the occupied states and the unoccupied states to correspond to the energy of visible light. And we prefer that they're at the same K point, which is called a direct gap. The good news is that we were able to find that the band gaps all lie within the visible spectrum, and some of them were in fact direct. We took care to do these calculations with a hybrid exchange correlation functional named HSC06, which is known to give better band gaps than the standard PBE-based techniques. Next, we'll look at the energy associated with the excited electrons to ensure that they would want to leave the material. This is a necessary but not sufficient condition for the electrons to participate in the reaction. And what we found here is that the energies of the excited bands, as compared with the equilibrium energies at different reactions, point in a hopeful direction. The electrons may want to jump off of the material to participate in CO2 reduction, which is drawing back to the figure that I introduced earlier in the talk. Now, we'll turn our attention to the interaction of molecules with the surface itself. First, we'll use DFT to gauge the binding of reactants on the surface, namely CO2, COOH, and CO. In particular, we focused on the basal plane of the material because it was an easier place to start. Then we correct for the free energy contributions from vibrational degrees of freedom. And finally, we look at the reaction steps to determine the bias voltage that would have to be applied to make the entire reaction downhill in energy without considering the effect of photoexcitation. So in other words, you can think of this as the his dark materials part of the talk because we're assuming that this is all happening without illumination. We found that CO2 and carbon monoxide effectively don't bind to the basal plane, and that the intermediate COOH has a very, very high binding energy. This hypothetical overpotential, which is defined here as the energy that the electron would need to make this reaction downhill, is 1.61 eV at the lowest. We note that this is a very rough estimate that could change in many different ways when considering different active sites, the role of defects, or even photoexcitation. But for now, what this means is that we found the basal plane is unreactive. So as mentioned earlier, we only looked at the basal planes. MOS2, for instance, is a good hydrogen evolution reaction catalyst, but the basal planes are unreactive. It's the undercoordinated atoms at the edge sites that are active. So we'd like to continue looking into different kinds of these materials, such as how defects could alter the reactivity. We found preliminarily that vacancies tend to lead to stronger binding. We'd also like to look at the role that dopants could play in enhancing the catalytic activity of these materials. So in conclusion, for candidate two-dimensional phases of possible photocatalysts, we explored the thermodynamic stability by ranking the formation energies, and we looked at dynamic stability by computing the phonon spectra. We then calculated the material's ability to absorb light and checked the binding energy associated with adsorbates of interest. This gives us new targets for experimentalists to investigate and for computationalists to examine. And now a thorough study of the active sites and the role of defects in these new materials would be an entire study in its own right. So I'd like to thank my doctoral committee, in particular Boris Kaczynski and Tim Kaksiris, as well as Jenny Hoffman and Cynthia Friend, as well as the financial support I've received from CSGF over the years, including giving me such wonderful experiences such as my practicum. I'd like to thank the members of the group that I worked principally in graduate school, namely the Materials Intelligence Research Group at Harvard under the tutelage of Boris Kaczynski. Also, my summer at Berkeley was, again, an unbelievable experience that I'm still to this day grateful for. And Professor Pershin was obviously at the center of this experience. Since I was early on in my time in graduate school then, her group really modeled for me how a team can feel like a community of scientists that care for, teach, and uplift one another. And I've tried to model that in the groups that I've inhabited since then. Joey and Arunima, who I've worked for day to day, were also incredible mentors and sources of wisdom. I'd also like to thank the members of the group who helped make that summer so special and hospitable. I'd also like to acknowledge that I spent in summer, the other half of the day, doing an internship in the middle of the CSGF, where I'm going to be returning in the fall to work full-time as a research scientist. So I'd like to thank my principal advisors, Linda Hung and Santosh Saram, fellow CSGF fellow Aditi Krishnapriyan, as well as Matt Carbone, who is also presenting at this session because he's my same class year, not only in the CSGF, not only in graduate school, getting his PhD at the same time as me, but also we were classmates at the University of Rochester in 2016. So that's my talk. Thank you very much for your interest and attention. And at this point, I'll take any questions that you have. Thank you.